Okay, so recall the scenario for a binomial random variable. We define x as a random variable that is binomial if it has possible outcomes 0 through n, which are defined as the number of successes. So we're counting as we observe n repetitions of the same scenario. And we count the number of times we see a success. What is a success? It's what we're looking for. Okay, I define that as our outcome of interest. Either we can have a success or we can have the opposite or failure. That's only two possibilities. So that's the first criteria for a binomial. Second, every time we look for our success, we have a probability of observing our success. So this is known, or we can calculate it. So it's known, and it is important that we know that in order to determine the probabilities or expected outcomes. So we give it a label name. We call it P because it's going to be one of the parameters of the binomial distribution. And finally, we need to know the number of times we observe or look for our success. We know it. It's a finite number. You can't just know it and say it's infinity. It has to be a finite number, and it doesn't change. Okay. So we refer to the number of times that we repeat looking as the independent trials. Okay, so that was pretty clear. I don't know why I zoomed out there. Anyway, this got really big. Oh, why? Oh, well. Okay, so what is the result of that kind of setup? We are going to count, and either we can have no successes out of n trials, we can have one success, and we can have as many as all of them. Every time we look, we see what we're looking for and successes. All right, so what does that accomplish? So one example of this was, let me just jump over here, was this one, right? Where we talked about X being defined as the number of tails in 4 flips. Don't forget the 0, okay? So there's 4 plus 1 possible outcomes because there's the 0. Don't forget the 0. 0 is a possibility. And I listed here previously, I listed the possible outcomes. And because there were 16 and they were all equally likely, each outcome has a 1 in 16 chance of occurring. So when we did this problem, we drew it out, we discussed it, and I was able to group similar looking outcomes and define 0 tails, 1 tail, 2 tails, 3 tails, and 4 tails. And this is like a very manual, very what am I going to say? It's not a systematic way of solving this kind of a problem, right? We're going to go problem by problem and do this, make lists and figure it out. It's fine. You can do that, but there's a more systematic way to approach this. If you have the 3 criteria of the binomial, you can use the binomial formula. Okay, the binomial formula looks like this in the box. Where does it come from? I'm going to describe where it comes from, beginning with one example. Okay, so we're going to begin with this outcome here. Okay, I'm going to begin with that outcome, and we're going to discuss it. And then you're going to, from there, attribute that in general. We're going to talk about it in a more general way. All right. So let's look at that. The outcome of tail and head and head. How would we find that probability if we had no concept of the context and the big picture looking at us? If I need to find the probability of this, I would write probability tail and head and head. And remember that when I have an and, I can multiply if what? When can I multiply all of these together? What's the requirement? When can I multiply those together? What's required? You can put it in the chat. Juliet knows that they're independent trials. What does independent mean again? In this, not that one does not affect the other, but seeing a tail doesn't change the chance of seeing a tail on the next time. That's what it means, being very specific. See, observing a tail doesn't change the probability of a tail on the next one. It stays the same. In other words, P does not change. Okay, if you remember the class last week, P does not change. P stays the same. That's what independence is. So since they're independent, I can just multiply these, and the probability of a tail is what? I define it up here. The probability of a tail is 50% because each time I flip, there's a 50% chance that I get a tail. 50% chance that I get the other one, or the failure, the head. So that's 50. So that's the P. This one is 50. That's the P. And what is head? What's the chance of a head? $50. Right. So it's 50. So this one is a little, it's unique in the way that the number of P and which is the success and the failure are the same number. But I use this example because we spent some time on it before, and I don't want to, introduce another example and when we know this one very well, okay? But I could do this for another example for sure. All right, so we define X as a binomial with N as 4 trials of repeatedly flipping a coin, and it's 50% chance of getting what we look for, the tail. So I've now figured out that this probability is 0.0625 in another way. We know the chance is 1 out of 16. Why do we know that? Because there's 16 possible outcomes. They're all equally likely. And so because the probabilities must sum to 1, 1 out of a 16 times is 1. All right, so that's why that was the way we figured it out before. This time we did it a different way. We did it this way, step by step. Okay, so that's like a second way to do this. What did we find? Let's write this in symbols. Okay, let's write this answer out in symbols. So our P is the probability of a success. I convert these two here into P times P, or P squared. Is everybody okay with that? And the probability of a head as the opposite, or the complement of P, as 1 minus P. And there's 2 of those, 1 minus P squared. Any questions about that so far? So rather than getting the numbers, I want the symbols because I want to make a generalization.
I didn't get that part, Professor. Can you say that again?
Okay. So now I'm going from this example, I want to interpret in symbols because I want to generalize, right? So probability of a tail appearing on each trial is P, and there's 2 of those here. So it's P times P, which is P squared. Is that okay? Then what is the probability of a head? If the probability of tail is P, the probability of head is the complementary event, which is always 1 minus the probability of what you're looking for, 1 minus p, and there's 2 of those. So I write 1 minus p squared. Is that better?
Yes, thank you.
Okay, so I have success times failure in terms of the more general notion of what we're doing here. And these are the numbers, and I know how to calculate it, but I'm more interested in the formula here. All right, so the next thing to do is talk about, well, that's the outcome of this one here. But how many ways are there to see 2 tails? How many ways? 1, 2, 3, 4, 5, 6. Is there a systematic way to know that if you repeatedly do something n times and you know the probability of seeing a success each time you observe, is there a way of knowing how many different arrangements there are of seeing what you're looking for? Because these are essentially, in the context of the problem, these are all the same thing. That's why we group them together. 2 tails. There's 2 tails here. There's 2 tails. It's just the arrangements of observing them is different. But we're not interested in the arrangements. We're interested in only to list them. We're interested in the fact that there's 2 tails all the way down. So is there a rule or an easy way or a systematic way to find its 6 without making the list, writing them all out? In fact, there is. And this is something you should have learned in high school. At some point, some people will say, high school was a long time ago, and that's okay. But I'm going to remind you or show you now if you never saw it. This is called a combination. And we can calculate how many combinations there are for this event outcome by using this. This is called a combination of how many ways, this is answering the questions, how many ways are there to see 2 successes in 4 tries? Now notice this is a big bracket. This is like a vector. You know, you might have seen something like that. You don't divide them. Okay. In fact, this symbol is a combination, and the formula to solve it is with factorials, something else you should have learned in high school, which you might not have learned. But you don't have to worry because we have this on our calculator, all right? Or you can even use Excel to get this. So this is known as, we call this 4 choose n, or in more general terms, I refer to it as n choose k, n choose k. And I wrote it here, 4 choose 2. And the answer for it is 6. 4 factorial is actually 4 times 3 times 2 times 1. The factorial, this exclamation mark, just means keep multiplying all the way down. This technique or this kind of math is used in probability, right? You don't have to be a probability expert. I'm going to show you how to get this number out of your calculator in a moment. So what do we have here? Let's go a step back before I get into this. What we did was we calculated just this here, and we found that it is p squared times 1 minus p squared. The 2, a little bit unfortunate because they're the same number and it's hard to distinguish. I want to write it in symbols. The 2 was the number of successes. So I'm going to refer to the number of successes with the letter. Does anybody know what letter I'm going to use for that in my formula? What is the number of successes in the formula? Brian, Juliet. Okay, so you guys read ahead. So K, you know Kellogg's Special K? Special K, I'm not recommending you eat Special K. I'm just going to hope you remember the K is special, and it represents, out of all the possible outcomes that are possible, 0, 1, 2, 3, 4, the K represents the one that we want to compute, okay? Because these make a probability distribution, and we just want one of them for now as our outcome. And that's going to be the K, the special K in the formula. So that's why I write here K, okay? That's the one we're looking for. So in this case, we're looking for 2, this is also K here, 2 successes. So if 2 are successes and we try 4 times, how many failures are there? Well, in numbers, it's 2. But in symbols, we write N minus K. Why do we write N minus K? Someone tell me, why do we write N minus K? I can't put it together.
Because if N are the trials
Yeah,
and K are the successes, then when you cuando lo resta,
exacto.
whatever is left should be failures.
Exactly. Okay, so this is not so hard. It's not so hard. I'm going to show you how to do it with words in your mind, not to get caught up in the symbols. Because if you don't understand this and you're just copying, it takes a long time and you easily make a mistake if you don't know what you're doing. So it can make a lot, you can have a lot of opportunity here for mistakes. All right, so K is the special one we're looking for. We're going to try N times. So that leaves resta, right, is N minus K. So this K, when you look at it, is successes, and this N minus K is failures. The probability of failure is 1 minus P, and we're going to multiply because of independence, failure times failure times failure. And here we're going to multiply the successes, success, success, success. And we're going to multiply by how many times it's possible with this thing that I just introduced. All right, so let's look at our calculators. Let me get onto my, I'm going to get onto my calculator and show you how I easily do this. Now you're going to have to locate that on your calculator. I can also show you in Excel if you didn't want to buy a calculator, but I do recommend the calculator over Excel. I mean, Excel, everybody has it anyways, but having the calculator makes everything so much faster. Makes everything go so much faster. Let me set things up here. So there are many different kinds of distributions. We just focus in this course on the binomial. You become an expert of the binomial in this course. And I also mentioned hypergeometric, Poisson, just as examples of other distributions that people might confuse with the binomial, but they're distinct and they have their own parameters and they have their own function in Excel. Okay. So let me project. So we have so this is N choose K. We say N choose K. In our example, we want 4 possible outcomes, and we want to know that 2 are successes. Okay, so this actually is like that formula that I put in the notes, but you don't have to worry about that because oh, sorry, I want to go to my calculator. We write this in symbols with like a vector, but you can also write 4C2. Now, do you see that anywhere on the calculator where this is N? And unfortunately, they don't use K on the calculators. They use R. And I don't know why, but I'm trying to think of why they use R. But anyway, that's the symbol. So do you see that on your calculator? Do you see that on my calculator? Where is that? Here, right? Above the plus. You see that? So I'm going to press 4 second function, NCR 2. And when I press equals, what should I get? What answer do I expect? How many ways? So this is the number of ways. So NCR or NCK is the number of ways of seeing K successes out of N trials. That's the definition there. How many ways do we expect? Oh, let me check the chat. 6, very good. So you guys are paying attention. So this should be equal to 6. Let's check. Equals 6. That's it. I'll do it again. For second function, NCR 2 is 6. So this helps us know how many different ways, in a systematic way, it helps us know how many different ways there are to see two tails arranged or rearranged in 4 trials. What do we do with that number now? We just multiply it. We just multiply it by the probabilities. Okay, so let me get out of here. If this is okay for now. We'll go back there in a moment. So I found out that this whole thing is 6. I multiplied by 0.5 to the number of successes and times 0.5, which is the probability of failure, to the number of failures. And you multiply all of these together and you should get this number, 0.375. So this is the this is a systematic way to get the answer, right? So from now on, when you see a problem that is set up as a binomial, you can use this formula, which shouldn't be hard. It should be helpful, right? Remembering what we did in module 6, we developed this whole probability distribution manually by making a list. And making a list is feasible if you have 4 outcomes. But what if you have 4,000 outcomes? Are you going to do this? Are you going to make a list, writing all the possible outcomes and counting? And no, because why would I have 4,000 outcomes possible? Because we use the binomial theory for sampling. We use the binomial situation for sampling, for finding out or making inferences about what to expect given results of a sample. Or say, given, well, we're going to do this 2 ways, and I'm going to explain it later. But one that I'm trying to describe here is if I give you the probability of seeing a success, you should be able to predict what you would see in samples. That's the first step. And that's what we're focusing on right now. I give you the P, and you can calculate, if it's a binomial, you can calculate the probability of seeing a certain outcome in the sample. Now, that doesn't seem very, when you think about it, why are we doing that? Suspend judgment until the end. Okay, we need to finish the course for you to see what we do with this. But right now, you're just practicing. Have you all seen The Karate Kid? Hopefully, you've all seen The Karate Kid now, or Cobra Kai, right? You repeat a motion for you don't know what purpose till the end. You have an instinct to use it. Okay, you have the instinct, and that's the idea here. We're going to practice doing this, and then we're going to use this concept for more realistic situations. Let's say it that way. Okay, so we're practicing applying this formula. So this one is in decimals. I put it here. It's 0.375, which we figured out before, but now we've approached it from a different angle, okay, using this formula. So this is actually the binomial formula with different Ks. This K is 0, and it looks like this, 0 here. So this is, we want 0 successes. So n trials, n choose 0 successes. This is probability of success to the number of successes, probability of failure to the number of failures, and that's for 0. For 1, so all that's changing is the exponent, and here this is changing, and then here n. Okay, so that's the whole distribution has this pattern. And if you remember, and so this is just me discussing to derive it again. I just describe it again. So if you remember this example for the number of flips that are tails, or sorry, the number of tails and 4 flips of a coin, if you remember the picture for it, let me go back and get it. In the notes. It looked like this. Everybody remember, hopefully? If I graph it, it looks like this. This is from page 16. What did you say? You told me, what did you see here when you look at that? How can you comment? How do you describe what you're looking at to someone who can't see it? Either they're away or they don't know what to see there. It's symmetric, right? Not necessarily normal, but symmetric. What's in the middle is mirrored. You can mirror from the middle, this side to the other side. It's symmetric. It's actually exactly symmetric. And you can see that here also in the distribution. Remember, it's a discrete distribution. There's only 5 possible outcomes, and their probabilities sum to 1. So it's symmetric. Okay, here's the question. Will a binomial always be symmetric? Yes or no? If I change, going back to our notes, if I change, let me close this. Close this. It depends on P and N. That's why they're parameters, because everything depends on P and N. Okay, so it could be symmetric. So let's talk about when it's symmetric. In this case, it's symmetric. The reason it's symmetric is because P was 0.5. So if P is 0.5, the binomial will be symmetric. That's one condition. So keep that in your mind, okay? If P is equal to 0.5, the binomial will be symmetric. The binomial distribution, I'm just putting it in the chat, will be symmetric. But there's another situation where the binomial will be symmetric, and it comes up in the notes. I do mention it, so I'm just gonna put them in the chat. Actually, I'll put them on my iPad. Let's do that. I'll put them on my iPad. Okay, so Binomial distributions are symmetric if either one, P is equal to 0.5 or 50%, like we just saw in the example. And the second condition, which will come up again in this module, and it's not so easy to see right now, but we're going to use this property. If the combination of N and P is such that N times P is greater than or equal to 10, and N times 1 minus P is greater than equal to 10. Okay. Again, it's not so intuitive to understand why. But the thing to remember is it's a combination of the two. If the combination of the two is such that you have enough repeated trials and P is big enough at the same time or balanced enough at the same time so that the multiple is more than 10, you will have a binomial that is actually symmetric. And in this case, it's even more than just symmetric. I'm going to make a specification. If it's just that P is 0.5, you're going to see symmetry. But if this is the case, you're going to have a stronger set of information or more rich information because the distribution is actually going to be approximately normal. Why are we happy about that? Well, you'll see, but we know the normal distribution. You spend a lot of time on the normal distribution and it's going to be worth it. And if you didn't spend a lot of time, go back and learn the normal distribution because it's going to be worth it. Because in the end, we're going to use it a lot. We're going to rely on it. It helps us make predictions, right? And alleviate uncertainty. I have a lot of noise behind me. I don't know if you can hear that. It's distracting me. Okay. I think it's quiet now. All right, so that's where we're headed. Let's get back to our problem. You'll see this again, so don't worry if you don't get it, but you'll see that again. All right, let me stop sharing. Did you copy that? All right, so for now, this is a little bit intimidating, I guess, when you see it the first time, but I want you to see is that for every probability, it's the same formula. All that changes is the N across the top because the P stays the same for each example, right? For each distribution, the P doesn't change, just the N. All right, so here I describe it again if you didn't understand what I said. Let's just apply. I'll come back here later. I want to just apply this. I have some examples here that you can read through, but I'm going to skip over it. Well, no, actually, I'll do this one just to help you understand what you're seeing on your calculators. And then I got to show you in Excel too. We did do this in Excel before, but I want to show you again. All right, so this example was introduced back in module 7 or module 6 about an experiment where 100 cards are presented to an individual, and we're going to test if the person has extrasensory perception or ESP. So they can basically read minds. Okay. How do we know they have ESP? We are going to set up we're going to set up the experiment, and those cards, 100 cards, have 4 possible outcomes, each equally likely. Either the card has an image of a star, a circle, a wavy line, or a square. The condition for having ESP is that half of the cards are correctly guessed. And the question I ask you is, what's the chance that a person who is just guessing actually is found to have ESP? It should be pretty rare. Not, a lot of people shouldn't have ESP. It should be rare, but with that standard, what's the chance? Is what we want to figure out. So what's the chance of seeing a correct guess? If there's 4 possible outcomes and each is equally likely, and the total of the probabilities must sum to 1, it means that each is 25% or 1/4. So it's just like we talked about with the flipping of a coin. Is 1/4. In this case, flipping of a coin 4 times, looking for a tail, we said there were 16 possible outcomes. And so one of the 16 was the probability of any of the 1 outcomes. In this case, it's going to be 1/4. Does everybody understand why it's 1/4? Do I have to write it out? Does anybody want me to write out why it's 1/4? So, so there's 4 possible outcomes, each equally likely. If they're each equally likely, and if they're equally likely, then the probability of seeing it times 4 must be 1, right? Because the probability of each one, I'm just using the word probability. Right? It has to equal 1. So 4 times probability is equal to 1. So the probability must be 1 divided by 4 is equal to 25%. I mean, I'm saying more than, okay, so just that's, and you remember this when we did the uniform distribution too, the concept there? Okay. All right. It's easy enough to show you, but at the same time, it's really important that you have those basic concepts because I use that repeatedly. Let me get back to the, I don't want you not to understand because I assume that you understood the basic stuff. All right, so that is 0.25 for each possibility. We're going to try 100 times. So X is written as distributed. Remember, the symbol means distributed. Binomial, N is 100, P is 0.25. And we are going to figure out what's the probability in different cases. We want to know what's the probability of guessing at most 2 cards correctly. So at most, where the possibilities are what? Remember the 0, no successes, no correct guesses, up to 100 successes. So which of these possible outcomes are we interested in if we want at most 2 cards? 2 or less. So we want to calculate the probability of no successes, 1 success, or 2 successes. So we're figuring out in this table just the first three. All right, we're going to figure out the first three. I can generate the whole table in Excel and just add up the first three, but I want you guys to learn the formula. So I plug in for the formula 3 times and choose no successes, probability of a success to the power of the number of successes, probability of failure to the power of the number of failures. And I'm going to do this on my iPad in another example. I just want to show you now. Let's plug this into our calculator and see what we get. And what in the world is this number? Okay, so let's do that together. I'm going to copy that onto my iPad and we're going to do this together. All right, so there's the problem. I'm going to use my calculator. And I'm going to I'm going to just punch this in first I'm going to do it from left to right, and then I'm going to show you an easier way to do it. So I'm from the beginning. I'm going to pick 100, second function, NCR 0 equals, well, I actually don't have to press equals, but I want to show you that it's just 1. And I'm going to talk about if that is always the case when we choose 0. Okay, we'll talk about that. Times 0.25 to the power 0 times 0.75 to the power 100. Now, this is only going to work if your calculator is in order of operations mode. If you need to know how to do that, let me know. I can help you set it up. And I get this. So this is the answer in the notes, 3.207 times. So what does that mean? Let me write it out. That means 3.21 times 10 to the power negative 13. What does that mean? That's what it means, actually, right? The negative 13 there means that you take 10 to the power negative 13. So what does that mean? That means that you need to take this number and put 13 decimals on it. So it's going to bring it to 1 decimal. So it's going to have actually 12 zeros in front. So the actual number you're staring at is, now obviously the engineering students will know this. This is for the non-engineering students. It's going to have 12 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, like this. For all intents and purposes, this is just 0, okay? So I'm going to say any number with more than 4 zeros in front of it is going to be 0. So if anything says like 6 times 10 to the negative 5, that's going to be 0. Well, I'm going to say 5 to the negative 5 because that's what you're looking at. Okay, so if you have a negative 5 here, you're basically staring at a 0. So for probability, anything with, I want you to always write, okay, 2 things. One, I want you always to write 4 decimal places. Okay, from here on out, if you have a probability, summarize it with 4 decimal places. That's how I do it in my notes. If I was to summarize this with 4 decimal places, this number would just be 0.0000, right? So another way of saying that is if this has a negative 5 or more on it, it's just 0. Okay, so don't get intimidated by these numbers. It's just 0. So because of what I get here, this is just 0. So in other words, it's small, right? It's very unlikely that if somebody's just guessing cards, that they will get none of them right. They're going to get some right by just guessing. There's no, here it's saying there's no chance that they're going to get everything wrong. They're going to get some right. Okay, so from this takeaway is just, if you see a number like this is just 0, how do I know it's 0? Because it's more than -5. It's more negative than -5, so it's just 0. In numbers, if you see any number like this, that's just 0. It's small. Questions? If you, to remember about the calculator, to put it into order of operations, you have to hit second function, format, and you have to scroll down with the arrow until you see this. It has to be an AOS. This will be the proper order of operations. It will preserve PEMDAS, in other words.
Professor,
Yeah,
can you, I have it on AOS already.
that's good. That's what you
And
want.
okay, and can you show again how to enter
Yeah,
the
okay.
formula?
Okay, I'll go slow. So 100, second function, NCR 0 times 0.25 y to the x 0 times 0.75 y to the x 100. Again?
Got it.
Is that
Yes,
good?
got it.
Okay. Okay,
Thank you.
so if you have it in AOS, it's easy. If you don't have an AOS, it might mess up. Okay. I want to show you just an easier way to do this. Before you enter anything in your calculator, you can, most of the problems simplify very easily. Okay, most of them. Anything with a 0 and choose 0 will always be 1. And I'll explain why in a moment. Any number to the power 0 is always how much? 1. Okay. And so this problem is just 0.75 to the power 100. So it's much easier. Now let me talk about why is 100 choose 0 always 1. I'll talk about that. And I'll leave the rest for you guys to play with on this topic. Just point, you're going to use this key for the powers, right? Y to the x. Okay, let's talk about why is 100 choose 0, 1. I'm going to do not just 100. I'm going to talk about n choose 0 as 1. Okay, I'm going to go to a simpler case because I can't write out 100 very easily. It takes a lot of time. Because what I need to do is consider all possible outcomes. Okay, so let's go back here as my example. In fact, for this example, I'm going to use n of 6 because I can work with 6 easily rather than 100. In fact, this is called, this thing, the choose function here is called the binomial coefficient. The binomial coefficient. And again, you don't have to worry about all these symbols here that come from probability and mathematics. Just know the name is binomial coefficient. And the binomial coefficient n choose 0 in general will always be 1. Doesn't matter if it's 6, 100, 10,000, n choose 0 will always be 1. Similarly, n choose n will always be 1. So notice here, I have 6 choose 0 is 1, but at the end over here, 6 choose 6 and 1, and there's perfect symmetry. It goes 1, 6, 15, and it goes down 15, 6, 1, and then 20 is in the middle. So it's symmetric in the coefficient. What changes the binomial formula or the distribution ends up being the P. Right? The P is what's going to change things because the N doesn't matter what N it is, it will always make the coefficient here symmetric. And the first will always be 1. Okay, so let's talk about why is that 1? Why is that 1? Does anybody want to try and explain it? Or do you want to leave that to me? what are we looking at? What does it mean? N choose K is the number of ways of seeing. Let me share my iPad. So N choose K is a number way of seeing K successes in N trials. So in other words, so let's just do, for example, 6 choose 0. 1, 2, 3, 4, 5, 6 possibilities. What are the possible outcomes? S or F, right? Failure or success. So I'm going to put here, this says no successes. What does that look like? What does no successes look like? F, 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 F. How many ways can I arrange the Fs? One. That's it. Okay, so that's why it's always going to be 1, because if they're all Fs, there's only one way to see it. You can't, these are all the same thing. And if I rearrange them, it doesn't change it. Okay, so it will always be 1. Let's do 6 choose N. What will that be? So probability theory or probability calculations depends on doing this kind of thinking process. But if you can find a pattern, you don't have to do this every time. And that's why we program into calculators this whole choosing function and choose K. It says choose. Okay, so how many ways are there to see? Well, I'm not going to put N here. I'm going to put, in our case, what's N is 6, right? So I got to put 6. Sorry about that. So 6 choose 6. How do I write that? So this meant 0 successes. This means 6 successes. How many ways are there to see 6 successes in 6 tries? What is a success? S, 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 S. How many ways to see that? 1. All right. So that's why it works like that. All right, let's go to the next step. Let's see, is there a pattern in general for 6? So let's summarize. So 6, no. So N choose K is equal to 1 is equal to N choose N minus, what did I just do? Not N choose K, N choose 0. Let's put 0. Is always 1. And N choose N is always 1. That's what I just proved. Does everybody agree I proved that? I proved it. I demonstrated. Okay, so this is behind what we're doing, but now that we get it, we can just remember this. Let's do and choose 1 now. Let you try it yourself. What about and choose 1? Use the example of 6 again. Now, you could put it in your calculator, but I'm trying to get you to see the pattern so we can generalize. So we're gonna have 6 spots. 1, 2, 3, 4, 5, 6. Sorry, I have a hair on my iPad screen. So this says 1 success. How many ways to see 1 success? Well, it can be success and the rest are failures. But also, I can write that as failure. And then the next one, so basically I can scroll the S through for how many possible ways? You see? How many? Okay, so you're just taking the S and putting it through. So I'm going to leave it for you to think about, but I'm going to write this as N choose 1 is always N, correct? Right? And then also N choose N minus 1 is always N. It's going to be symmetric. So for our example, I won't test you on this. I'm just trying to make it easier. You see how I do things so quickly is because I always remember if I put a 0 or an N here, I'm always going to have 1. And if I have a 1 here or 1 less than N, it will always be N. It's just something that makes all the calculations so much easier. But you don't have to use it. If you just use your calculator, you just Excel, it's fine. But it's actually very elegant and very beautiful to see these patterns. Well, anyway, I think so. 6 choose 5 should also be 6. This means 5 successes. So it's going to be the inverse of this pattern here where I put 5 S's and 1 F. It's the same thing. Because there's 1 F, you scroll it through and there's only 6 ways to see that. Got carried away there. I'll leave it for you guys to do that, but that's how the pattern works. Okay. All right, so now let's solve some problems. We spent a lot of time talking about the formula. I hope it didn't confuse you. I'm going to jump over all this stuff. You guys can read that as background, but let's do the problems because if we spend about a half an hour on the problems, then I can get to SDS and the highlights. I feel like the highlights are helping you. I hope they're helping you. It always seems like there's more material than the highlights, but don't lose sight of the highlights and you can get through the material that way. My husband doesn't watch sports anymore. He just watches the highlights and he's satisfied. It saves him a lot of time. I do want you to, then he'll go back and watch some games, the ones that he needs or he feels like he really wants to watch. In this case, I want you to go back to the notes and fill in the gaps of your understanding. Essentially, you need to solve problems, right? This is the goal. So we want to make this as practical as possible. Okay, so I'm going to get out of here and go solve some problems. After all this chatter, I'm going to jump over all of this. This is for you to read and, practice. Oh, let me just talk about this for a moment because this is going to be the next part. This is to motivate. Sorry, you can't see this. This is to motivate you for SDS, sampling distribution. In the same problem about the testing for ESP, I want to solve what is the probability that somebody will actually be found to have ESP. Remember, the definition of ESP is that they have to have 50 or more correct guesses. That translates into us writing 50, 51. We have to add all those probabilities together. If we were to just use the probability distribution, we would have to calculate the probability for each case. Now, because we have Excel, this is not so hard. It's not impossible. We could do this. I could generate this and I could add all those probabilities together. But before computing was widely available to people, like when I started, when I came out of high school and took statistics in the 80s, computers were not ubiquitous. They weren't everywhere. And so instead of using Excel to solve this, we actually had tables. And even then, reading 51 numbers off a table and adding them on your calculator is like seems like a waste of time. So what statisticians did was use the idea that the binomial becomes like the normal distribution in certain cases, and they made calculations using the normal distribution as approximations. All right, so that's something else I'm going to teach you, that link between binomial and normal in certain cases. What was the case again? If n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10. It's a very specific case, or a set of cases where that happens. So do you guys want me to show you Excel again? Or are you guys good with the Excel? You okay? You want me to show you again? Put it in the chat if you want me to show you again. Before I jump into using the formula. Okay, so you guys don't want Excel. So you guys can do that in Excel if you have to, right? But let's do this manually for a set of problems. We can do about 3 or 4 problems. We're going to start with this one. I'm going to ask you to read the problem. Try and solve it. You're not going to appreciate it unless you struggle yourself. This is always the case. So I want you to try and solve the problem without me. And then we'll talk about it. I'll give you 5 minutes. You can take a break, get some water, have a snack, be back here just before 10:25. Okay. I'm going to pause the video recording. All right. So I'm going to write out the problem here. And I'm going to show you a systematic approach to applying the systematic formula, systematized formula. Let's see. Okay, so what I'm going to do, I rewrote it there. And I'm going to ask you for X and P, K, and ask you what is a success. So in this problem, I want you to find those 5 things. What will X be equal to? What's N? What's P? What's K? And how do you define success in this problem? In other words, what are we looking for? So what event are we repeating? Let me check the chat. What event are we repeating? Rolling dice. Okay, so we're repeatedly rolling dice. How many times? Six. Okay, so N is equal to 6 repeats. All right. And each time we roll the dice, what are we looking for? Excellent. You guys are good. So seeing a 5. Okay, so seeing a 5 is a success. So we could either have no 5s, 1 5, 2 5s, 3 5s, oops, 3 5s, 4 5s, 5 5s, or 6 5s. Those are the possible outcomes. P is the probability of a success. What's the probability of a success? In other words, what's the probability of getting a 5 each time? Very good. 1 in 6. Now we have to leave it as 1 in 6. Some people might not like fractions, but I'll make you like fractions, or I'll help you like fractions. We have to leave it as 1 in 6 because this is a repeating decimal and it's hard to know. I mean, I could write it approximately as 0. What is 1 out of 6? It's 1616, I think, something like that. Yeah, 1666, right? So this is like 1666, like it repeats. I can write it like that. Or if you use my rule of 4 decimal places, you can write it like, let me fix that up. I can write it like this, and I put this because approximately, right? We want to avoid decimals when they're repeating. I'm going to say use the fraction. Use 1/6. Okay, so
Profesora,
yes.
yo también de primera intención dije 1 de 6 la probabilidad, pero me surgió la duda porque si tenemos en X es de 0 a 6.
0 a 6.
Sería como que era 6, no, 7, no es 1 en 7.
Hay 7 posibilidades
Yes.
si hay 6 repeticiones. Otra vez, pregúntame otra vez.
So the probabilities of success will be getting a 5 at some of the 6 rows, right? But it could be a time when we don't get a 5 at all. So that's why we
Exactly.
have a 0.
We're yeah, let me finish and then you can ask the question. Let me finish here.
Okay.
Because yeah, there's lots to think about here, right? There's lots to think about and we're going to simplify everything here. All right, so
But still, it's the correct probability will be 1 out of 6.
1 out of 6.
Even though I can
Each
get
time, cada vez. Don't worry about the big picture. Right now, cada
Okay.
vez, it's 1/6. The formula will get the big picture. Okay.
Okay.
But cada vez, that's all P is. Cada vez no cambia, es siempre 1/6.
Okay. Yeah.
1 divided by 6. Okay, so the special K. This is the punchline. What is the special K? How do I find what the special K is? Exactly 1/5. So K is just this one. I don't need the whole distribution. I just have to find where K is 1. Okay, I don't need the entire distribution. So all I have to do is apply the formula, probability, X is exactly 1. Remember, for the discrete distribution, we can do that. And the formula is like this. I put the bracket for the combination. 6 possible outcomes. I want the number, I want how many ways is there to see 1 success and 6 possible outcomes. And then I multiply by the probability of success. Okay, let me write the formula above, just to be, for people still not sure what I'm doing. And let me go right under. I'm going to move this right here underneath here. So the number of trials, the success I'm interested in, just 1 success. Then I take the probability of a success, which is 1/6, to the number of successes. And then, so that's easy, right? This is the probability of success, P, to the number of successes, 1. And here, whatever I put here has to make 1, right? Because this is a success. This is the failure. So what is the failure? 5, 6. And over here, whatever I put in the exponent must sum till n. So if it's 1 success, how many failures? 5 failures. Okay, so these exponents must sum to n. These numbers, the probabilities must sum to 1. So rather than, you know, making 1 minus in here, just put the number that makes them sum to 1. And here, rather than thinking n minus k, just, you know, if there's 1 success, there's 5 failures out of 6. Okay, let's simplify before we put it in the calculator. Okay, first of all, any questions about what I did there? Notice this is not a fraction, right? This is 6 choose 1. This is the binomial coefficient. What did we learn about when it's a 1 here? What did we learn the answer is? 1 success in 6 trials. 1 success in 6 trials. You were putting the S through all the trials. It's 6 ways, right? So you can even find it in your calculator. We'll do both. This will be 6. This will be 1 out of 6, and this will be 5, 6 to the 5. So how does it simplify? That's that. So we're going to do first, we're going to solve this with the calculator. Then I'll go back to the top and show you. You can get the same answer if you just plug it in blindly, like without simplifying. So let's just do this one. So 5 divided by 6. You have to say equals. You have to close the bracket. And then y to the x 5. And that's your answer. 0. And always take 4 decimals. Even if your options have 2 decimals, just always write 4 decimals. That's how my answers are. Now let's repeat. So when you solve problems in statistics where you don't have the answers, try problems different ways. See if you get the same answer. You know you're on the right track, right? You have nothing to compare to if you don't have the clave. Do it 2 ways. Let's also solve it from up here. I'll give you a moment to try by yourself to put this in the calculator the way I showed you to see if you get the same thing. I lost the 1 somehow. I erased it. These sum to 1. There are fractions, a few examples with fractions in this module, but don't worry too much. I mean, it's not going to be all fractions. I just know some people don't like fractions.
Professora, how do you did the calculation in the calculator for the
For this?
5? Yeah.
Okay, I'll do it again. 5 divided 6. You have to say equals. If you don't say equals, you're going to get the wrong answer.
Okay.
To the power 5, yeah, because it won't do it automatic unless you put the brackets around.
Okay, got it. Thank you.
You could do that too. You can say 5 divided by no, bracket 5 divided by 6 bracket, and then y to the x 5. You can do it like that. If you need me to do it again, just let me know. It's important. So for the test, I need you to write it down. You can use Excel to check your answers, okay, if you want, but you need to write it down as evidence that you know what you're doing, okay? So you have to learn how to do this. Excel is a backup. You have to show me you know this formula. It's a minimum expectation that you know the binomial. You don't have to know every distribution. You just have to know the normal, the t, the normal, standard normal, the t, binomial. Those are the most important. Those are the uniform, general probability distributions, very basic stuff. This is a good foundation to do other kinds of distributions if you're interested in continuing in statistics. I've had students take my class and then end up in a master's in statistics somewhere. It's not common, but it has happened. Okay, let's make the calculation from here. Okay, watch me first, and then you can try it. So from the top, without the simplifications, I'm going to say 6 second function NCR 1 times, I have to use brackets if I have fractions, 1 divided by 6, close bracket, to the power 1, which we all know is the same thing, but I'm saying blindly, you're just going to use the calculator, times bracket 5 divided by 6, bracket y to the x 5, and we get the same thing. So you should get the same thing. You can try it now. Just practicing using brackets. Again, it's just a foundation. Think of getting the instinct for doing this kind of thing is important in a foundation course. All right, so it's 40% chance. It's really high. I'm like doubting the answer right now. It's really seems like a high number. What the heck? So if I roll a die 6 times, the probability of getting exactly 1/5 is 40%. It's A. Okay, can everybody do that then? And that's your answer. The option is A. Any questions? Let's go to the next one. I'm going to skip number 2. And I'm going to jump to number 4. Okay, I'm gonna stop. Have you finished? Some of you are still copying. Are you finished with the iPad? If you need time, let me know. My hand is up. It's so funny. How can I put my hand up? Okay, let's look at number 4. I'm gonna give you some time. Try and set that up. The same as we did before, X and PK, success. Try and fill those in. X and PK, success. So if you're reading a problem and you're not sure it's binomial, you can still use the same approach. X and PK, success. If you can fill in, then you know it's binomial. If you can't fill it in, you know it's something else. All right. I should have stopped the. Okay, so people are writing things. Destiny. N is 7 and K is 6. Okay. Close, close, close. N is correct. K is partly done. Destiny. Hey, very good. So you guys are getting the idea. You're not stuck, right? X, N, P, K, success. I'm going to write down the important information. African hospitals treating patients who have Lassa fever. 70% of patients with this disease die. 70% of patients with Lassa die. Very scary. Each patient lives or dies independently of each other. Okay, now that's a stretch. That makes the math easy, but it's a stretch because if somebody dies in your household and this is a contagious disease, what's the chance that somebody else in the household will die? It will change, right? Because they had Lassa and somebody else can get Lassa and die too. Depends how you set it up, but okay. We'll just say they die independently if they have to be clear here. But in this case, they say it's independent, which makes our math easy. There are currently 7 Lassa fever patients in the hospital. Okay, so these are the main statements. And we want to find the probability that 6 patients or less die. 6 patients or less. All right, let me share my iPad. Yeah, so I took the important information, what I think is important. 70% of patients with Lassa die. What do I do with that number? What number is that? Or what is that telling me? Exactly. That would be P. Okay, so P is 0.7. So I get that. I'm approaching a different way. Let's put all the numbers in and then we can look at the whole thing. So P is 0.7. Each patient, as we look at them, the chance that they die, if they have Lassa, is 70%. 7 patients, it would be N. And what are we looking for? We're looking for, unfortunately, the death of a patient with Lassa. So X can be 0, 1, 2, 3, 4, 5, 6, or 7. Now it's easy to list it when there's, a few of them, but you'll see in my examples when I have like N is 100, I use the 3 dots, right? But here I can write it out. It's only 7 plus 0, 8 possibilities. So what is the special K? Which of these am I interested in? It says 6 patients or less die. So which of these am I interested in? 6 or less. 6 or 5 or 4 or 3 or 2 or 1 or 0. So I actually want all of these. That means we have to apply the formula 7 times. Or what's another way to do this? Remember what we learned with the normal distribution and what we learned in probability theory. We can use the complement. We can calculate for 7 only and take it from 1. That is the most tractable way. If you forget that you should do that, or you use Excel, you would just add them together from Excel. You can do that too, but you have to show me something, right, on your paper. You have to show me you applied the formula. So let's do this. 1 minus probability X equals 7. I'm going to put the formula here, remembering that probability X equals K is equal to N choose K, P to the K, 1 minus P to the N minus K. Maybe I'll get rid of my curly Ks. I'm just going to use a regular K. I have a habit to use curly Ks. So I have to take 1 minus N is 7 in this case, I'm going to use 7 as K. And then P, which is 0.7 to the success. And then that has to be 0.3 for failures, because that has to be 1. And then here has to be 0 for n equals 7. Okay, so that's how you fill it all in. They have to sum to 7. And the below have to sum to 1. We can put it in our calculator. Don't forget the 1 over here, the 1 minus. Or let's simplify. This one is very easy. What's 7 choose 7? 1. Remember? And what's 0.3 to 0? 1. And all this is 0.77. And there you go. So you should be able to do that.
Professor, one question here.
Yeah.
Is there any strategy that we can use to avoid repeat the calculations if we have a big X and a several amount of Ks? Like, for example, if this will be X goes from 0 to 100, and the K is something in between there, let's say that from 50 to 60, is there any, or from 50 to 75, something big? Is there any strategy that we can use instead of trying to calculate every X?
So I mentioned before that statisticians saw that in certain instances, the binomial looks rather normal. So they would use the normal, if the conditions applied, they would use a normal distribution. You'll see that when you get to SDS. So that's one strategy to add them all up easily, in a much more time sensitive way, or, in a faster way. But otherwise, the other possibility with current technology, you use Excel to add them up. Okay.
Oh yeah,
You use
worry.
Excel.
Okay.
But yeah, it's going to be the normal distribution. This is what they did before the 90s.
Mm-hmm.
Before computers were ubiquitous, we used tables. And tables, you can see, I have an example in the notes, but also online, you can get binomial tables that have been already, it's basically, they created the Excel table for you.
Yeah.
But the normal distribution is the way to do it. And we'll talk about that in the SDS.
Okay, thank you.
Yeah, but it's exactly what you have to think, like, because this is tedious, right? This is tedious. So statisticians found a better way, in terms of time saving way to do this. But still, I don't want you to forget the underlying formula. That's the important thing. Okay, so what did you get? You guys get some answers? Okay, so the probability that 6 patients or less die is 92%, because what did you get for this one here? 0.7 to the power 7 is like 8%. So it's going to be 1 minus. Remember, take 4 decimals, okay? 0.0824. That was a mistake. 0.0824. Don't forget the 1. So I'll put a negative in front, plus 1 is 90. So I write 90 0.9176, or you can round it because the options are just 2 decimals. 92%. Very good. Yeah, Maria, you just have the first part. Yeah, that's right. And then 1 minus 8% is 92. Now this one is tricky because the options are very close. You got to you have to be careful with your, keep the 4 decimals, and that will keep you on track to getting the right answer. So if you look here at the options, they're very close. 90, 91, 92. They even put 8 in there. Okay. So don't look at the answers until you're finished calculating to solve your problem. Don't look at the options. You might stop too early and pick 8. If you did a mistake in your calculation, you might pick 9. If you made a mistake in your calculations, but you did the 1 minus, you might have picked one of those. So this is very tight, very tight. Gotta be precise for this one. I don't have many that are that sensitive in the options. But this is just to emphasize keeping 4 decimals in your calculations. We're going to do one more, even though I said we would do something else. I'm going to do one more because I want you guys to walk away confident in binomials, okay? This is the feel-good portion of the course. Feel very powerful doing this. There are a lot of problems on this to practice with, and some you might have fun if you have time to work with the decimals. This is the last one. And these problems have been in my notes for years, but only since the COVID and COVID response have the word SARS meant something to any of my students. So SARS was around in the early 2000s, right? So that was like our first introduction to the virus, the coronavirus that we now know as variants of COVID. So here's my example. I want you to try this. I'll give you a few minutes to think about it. Okay, let's come back at 11:10 and look at this together. So try this one. We're going to finish with this exercise. Let's see. I'm going to write down the highlights. Okay, so this is probably one of the kind of more confusing problems, but there's not many of these. But once I do it, you'll understand. So we're going to use the same structure, X and PK. If we can answer these questions, we have a binomial. If we can identify these variables, we have a binomial. Okay, so there are 4 patients with SARS. So what's that? 4 patients with SARS. Okay. In a Toronto hospital who are monitored by 2 staff members. So I didn't use the 2 yet. Okay, but we're going to look at 4 patients, and then on the side, there's 2 staff members. So I'll write that down here, 2 staff members. I didn't use that yet. Suppose the probability at any one time of a patient requiring emergency attention by a staff member is 0.3. What is that? That's P. Okay, so let's take from that the words. Success is going to be, and I read it from there, and I also read it from requiring attention, right? Success is probability a patient requires attention. So that's my definition of success. Oh, sorry, not P, that's success. And just a success. Okay, patient requires attention is a success. Okay, so I have some lingering information here, but N is 4, P is 30%, X can be 0 successes, 1 success, 2, 3, or 4. What is a success? Requiring attention. So there are up to 4 patients that will require attention. Now, there's a kind of a twist in the question, the final overarching question. Okay, there's the events that repeat. Looking at the patient, you're going to look at 1 patient, 2 patients, 3 patients, 4, and see if any require attention. Out of all those attempts at looking at them, what is the probability at any one time that there is not sufficient staff to attend? Okay, so the question is, what is the probability of insufficient staff? Okay, now you got to translate it into numbers. Okay, those are the insufficient staff. When will there be insufficient staff? Let's go through the possible outcomes. Remember, these are the possible outcomes. Of what are the outcomes again? Requiring attention. All right, so if no one requires attention, is there insufficient staff? No. If 1 patient requires attention, is there insufficient staff? If 2 patients require attention, is there insufficient staff? So now you're at your maximum because there are only 2 members. So we're going to make an assumption here that's not clear, but assume each patient only needs 1 staff member to respond. Okay, so because sometimes you'll see 2 or 3 nurses or staff attending to a patient. We're going to assume if you have 2 people requiring attention, you only need 2 nurses, right? Because 1 each. All right, so if 3 patients require attention, do we have a problem? If 4 patients require attention, do we have a problem? So these are the ones we have to calculate to answer this question. Okay, so it's worded in a different way than the setup here, but we're going to tackle that. We're going to turn that into a problem for us by summing those 2. So K is 3 and 4. So let's do this, and then we're going to go. We're going to do this before 11:30. So everything, I think I had you until the end. Some of you get it because I gave you time to think it over and appreciate my answer. But the foundation, setting everything up, will help you to get to the realizing the terminology here is a little different, diverges from what we've said already, but you can flip it to go one at a time to identify which ones apply, okay? All right, so let's plug in the numbers as we've been doing. So this becomes 4, choose 3, probability of success to 3. So that's easy for us to do. Then we remember there's this failure. It has to be, this has to make 1, and this has to make 4. So that has to be 1 there. Because these have to sum to make n equals 4. Okay, then we're going to add that to 4, choose 4, 0.3 to the successes of 4. And I have to use 0.7 because these make 1. And I have to use 0 here because that makes 4. Now we can just plug this in. You guys can practice plugging in step by step to your calculator. I'm going to simplify. This is 4. And this is 0.7. That's going to be easy to put in my calculator. And this is 1. And this is 1. All right, so this simplifies a little bit before I punch it in to 4, 0.323 times 0.7 plus 1 times 0.3 to 4. So now that's easier. If you want to do the long way, it's fine with me, but I just want to wrap this up. Let's see if I have to go, and that's all you have to punch in. And you should feel proud of yourself if you're understanding. You should feel proud of yourself if you've hung in there, even if you don't understand. Punch those in and get me the answer. And then we're going to go. Okay, let me try it. Let's see, I have a dispute, 2 different responses here. Hopefully I did everything right. Let me verify. So I'm going to put 4 times 0.3 to the power 3 times 0.7 plus 0.3 to the 4. Now there's a lot of key punching, okay? If you're stuck on a problem and you can't get past it and you can't see what you're doing wrong, you're not getting the right answer, let me know. Take a picture, send it to me, and I will help you with that. I don't want you to get stuck. And that's what I get. Okay, so Eliximar has it. Maria has it. Destiny, what number do you have there? Did you do 1 minus? No, I'm not sure what you did there. It looks like you did 1 minus, but I don't know why. You don't have to do 1 minus for this one. Destiny, you just punched it in. The 1 minus was just for that special case. But good, if you got opposite, you're close. Oh, all right. Anyone who wants me to calculate it again, let me know. That's the whole problem. I think that's probably the most challenging one. They don't get harder than that in this class. That's challenging because the way I asked the question will diverted from the way I was setting it up. It was related, but might have been a bit confusing. Oh, I have a only needs. This says only needs. I hope you can read writing. I kind of write and I print both. I hope that doesn't confuse anyone. You can read my cursive writing. It's just faster. Okay, questions? I didn't put the final answer here. 0.0837. So the answer is B. E is the complement. No, you don't have to minus 1. You don't have to minus from 1. All right, so I'm going to leave you with that for the weekend. Do your best. to get through SDS, and then you can spend the week practicing. I guess you're supposed to be working on inference this week, but I see that most of you didn't start this. So get through this as fast as you can. So it's out of the way, because next class I'm going to burst into inference. You have 2 weeks to do inference. Let me think, hold on, because we are the 25th. Yeah, you're really going to have to start inference this week. You're going to have to get through this weekend and find a way to start inference. Let me talk about inference before we leave. Let me talk about inference before we go. So 40% of the final exam is on inference. So you really should be spending the next 2 weeks doing that. I hope I've given you a good start with the binomial and sampling distribution. You should finish that as soon as possible, because you really need to get into inference. Now, inference, you see, are lots of videos. They should be pretty good, but they are a lot of videos. So it's a huge package of notes if you're going to print them. If you're not going to print them, it's a bunch of videos, okay? And it's a lot of exercises. I solve a lot of problems. I do a lot with you. So that's why you need to get started as soon as possible. So if you feel confident about binomial, get into the sampling distribution, get through that as soon as possible, and get into these videos before we meet. I will do again next week. I will do highlight. Oh, somebody put a question about something. Just email me if you have questions. I can answer those by email probably, or direct you where it is in the videos that you can find it. But get started on watching these videos. What's going to happen in this module is I'm going to, and actually I do it in module 8 as well, is that I introduce you to my formula sheet. You're going to refer to the formula sheet that's found at the end of the notes, and I teach you from here. This is my summary. If ever there was a highlighted document, this is a highlight of the course here. This is what you'll need for the final exam. You'll probably feel like there's some formulas missing. You can add them. You can print this out. If you don't print anything else, just print this out. This will be your security blanket for the rest of the course, okay? So like I said, the finals in 2 weeks, you're going to know all of this. Now notice we already did number 1, okay? We've done that. The last statement here is what you're going to do in sampling distribution of a statistics. X has mean, NP, standard deviation, NP1. That is going to be discussed in the SDS portion of unit module 8. So you're going to cover that in SDS. You're also going to cover this in SDS, and you're also going to cover this. So the first 3 parts, half of it, you should finish this weekend, okay? That will be done. And then the next 2 weeks you're going to spend on this. And I'm going to describe these all in the videos. So get going on them. And in 2 weeks, you're going to be a quasi-expert. This is all you need. And you have you see things here. There's a lot of symbols, but you know some of these symbols already. We've seen P, we've seen N, we've seen Z. The only really new thing is T, and I describe that in the videos too. So this is it, big picture. This is where you're heading, okay? So print that out and have that at your side as you go through the rest of the course.
Where is this?
At the very end of the notes for module 8 and at the very end of the notes for module 9. It's right at the end. It's in the tables. The tables also, you should print these and have these at your side. But the most important I'm stressing right now is this one. This is where I focus. Last page. Okay, so you can print that. And if you get started right away, it's fine with me. I'll go through it all. So I understand maybe by the end you will not have finished inference by the time I give you the exam, but This is where you're going to find your answers, but you need to be prepared. Okay. So as soon as possible, begin inference. Spend some time with SDS. There's just a few videos there to watch. The summary is here on this page. I can't give you more than those 3 days for the final because the grades need to be posted. So we have to work with the deadline. All right. So if you can, take vacation time. If you can, lower your work schedule or delegate the work. But the next 2 weeks, you need to dedicate to wrapping this up because this is the culmination of everything. All right. And like I say, it's 40% of the exam. You can't forget everything else you learned, but this is 40% of the final. All right, so keep me informed. Do not delay. If you get stuck with something, let me know so you can move on. And that's it. My goal again is that you walk away with practical knowledge. All these formulas, some people, don't like the idea that I use these formulas, but it is a fundamentals course. You are in a master's program. This is basic. In fact, this material is the basics of a first-year course in statistics. Okay, I haven't done anything beyond that except expect you to have the ability to make practical interpretations more than a first-year bachelor student. What you guys are accomplishing. You're seeing the more practicality of it. But don't be hindered by the symbols. If you practice enough, you'll see the pattern. Wax on, wax off, wax on, wax off. All right. Okay, so we'll see you guys next week. I'm happy for you. I'm sure you got the binomial, at least to some extent. You're confident about that. Keep on swimming. Keep up with the material. All right. Have a good weekend. Bye.
Thank you. Bye-bye.
Thank you, Professor.
Thanks. Have a great weekend.
Gracias. Bye.
Professor, I had a question.
Sure. Go ahead.
Sorry.
Go ahead.
It was about the homework. I just let's start with that. I noticed that question 2, it was homework for binomial.
Okay.
Question 2 and question 11 seem to be the same. Is that so, or am I misreading something?
Let me see. Homework. Question. What did you say?
Question 2 and question 11.
Okay, let's see. If let me open it in 2 different windows so I can see. Okay, so that's that. So 2, the probability that a certain machine, let me pull this out. You guys can't see 2 at the same time. I can do it. All right, so if the probability that a certain machine will produce a defective item. What does this one say? The probability that a certain machine will produce a defective item. If a random sample of 6 items taken from an output of this machine, what is the probability that there will be 5 or more defectives in the sample? Yeah, I guess it's the same question. I never noticed that.
Okay, I thought it was crazy for a second.
I know. That's
just
fair.
wanted
I
to make
never
sure.
noticed that. I don't know how I haven't. It is exactly the same. The probability that a certain machine will produce a defective item is 1/4. If a random sample of 6 is taken, yeah, it's the same. question. Very good. See, he's seeing patterns. Good sign. I didn't even notice.
Okay, I
Okay,
just had
good. So
one.
sigue.
Sorry, what?
Go ahead. Any other questions?
Yes, I just want to see if you saw an email I sent you
Yeah,
on the
I haven't
web.
had a chance to look at it, but I will.
Okay, that was all.
You know
Thank you
what
very
my
much.
problem is, Alejandro, is that there's you and there's another Alejandro. And
Yes,
sometimes,
there's
and your name just says Alejandro and the other student has both names. So I'm I'm very careful about not confusing you guys, but I might have confused you. So I'll go back and look at it. Okay.
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 Thank you. Have a nice day.
You too. Bye. Bye, Juliet. Bye, Naisha.